welcome to its Language Technologies webinar series. Okay, so my name is Oyer López de la Calle, and I'm a lecturer at the University of the Basque Country, and I usually do research at ISHA and its centers as well. So today is my pleasure that we are having Desmond Elliott with us, giving a very interesting talk. And yeah, before that, I wanted to point out that we already had in this series some other interesting talks, like Heinrich Suche, Sam Bowen, and the others. Yeah, and these talks can be found in the webpage of its or our YouTube channel. Okay, so you can just access those. And then you can see also that next talk will be given by Dan Roth and Shakriani Sakti, the next one. Okay. So coming back to today's talk, Desmond is an assistant professor at the University of Copenhagen. He completed the PhD at the University of Edinburgh some years ago, and is there where I had the great pleasure to meet him. So I know him from that period. And I can say that his primary research interests are the multimodal and multilingual machine learning. And I think he's also well known because he was involved in the creation of many multimodal and multilingual datasets such as Multi30K or How2 and MaRVL. Okay, see, he is also known for co-organizing many workshops and shared tasks involving like a multimodal machine translation or how to challenge workshop and some other interesting workshops. Okay, and I think it's worth to know that some of his work received some awards or mention, like an area chair favorite paper at Colin 2020, 2018, and then as well he got the best paper award in MLP in 2021. Okay, so yeah, so that's all I have to say. So when you want, Desmond, you can start with your presentation. Okay, I might.
Thanks, Ayad.
Yeah, I think I should. Can you share the screen, Des?
At the moment, no, it doesn't allow me. Now it does.
Okay,
Now I'm allowed to do it.
good.
Okay, so I will share that screen, and then if I press play, I hope that you see a slide that's not the presenter view. Is that
Yeah,
correct?
it's correct. Yeah.
Okay, that's good to hear. So thank you, Ayer, for the introduction, and also thanks for the invitation. It's a great honor to be here today. This talk is about visually grounded reasoning across languages and cultures. And I want to start by highlighting what I think have been some exciting advances in this area over the last few years. There's been a huge amount of research on image captioning, a never-ending flurry of papers trying to build better computational models that either encode the image or try to decode sentences. We've also seen some great advances on reasoning tasks where models need to understand the combination of the language data and pairs of images to determine whether they are a true description of what we can see. There's also more recently been some exciting work on text to image synthesis. This was a project by OpenAI a couple of years ago where they showed that you had surprisingly good performance on generating images of things that were unlikely to have been seen before. And more generally speaking, we've seen the rise of self-supervised learning also apply to multimodal learning, where these models can be trained on one set of data in a pre-training phase and then applied to a variety of downstream tasks. And so what's really been at the heart of this work is the importance of having large amounts of data for training our algorithms. and this is common across all areas of NLP. Some typical examples of vision and language data that people have been using include the ImageNet dataset. This is a huge resource of annotated images that is mostly used to train visual encoders. And ImageNet is derived from the English WordNet hierarchy, where they try to richly annotate images across all parts of this dense hierarchy based on English language structure. On the side of data that's used to train multimodal models, we have the COCO dataset from 2014, which has 300,000 labeled images, and these images contain labels for about 80 types of commonly occurring objects. So things like frisbees or baseball bats or plates or bananas or tables or chairs. And so it's less richly annotated in terms of the number of classes, but there are more annotations per image. Another common example would be something like the visual genome dataset, where they have 110,000 really densely annotated images. You can see an example here on the right-hand side, where they have specific annotations with regards to the bench and the properties that it has. And these are derived from the COCO dataset and also this Yahoo Flickr 100 million images dataset. And so we've been doing some work over the last few years to rethink vision and language data. And one observation that might be obvious to some of you is that the data I presented on the last slide, which is really commonly used, is mostly in English. And in some cases, there are Indo-European languages as well for vision and language data. But even within those Indo-European languages, we notice some really strange things about them. Like this image here shows a vehicle on a street in a Dutch city. And when you ask an American English crowd worker to describe this, they have no idea what this is. But if you ask a Dutch person, then they immediately know that this is the draaiorgel. It's one of these wind-up organs that lives on the street, and they move it around. It plays some music, and they collect some money for it. So there's definitely a role of familiarity with the concepts that are depicted in those image examples. And this is something that could be explained by the sources of the image data. So like I said on the previous slide, it's mostly coming from ImageNet or COCO. And this typically reflects North American or European cultures. De Vries and colleagues had this great heat map of where images in the ImageNet dataset are coming from. And there's very little representation in South America, Africa, Asia, Australasia, or Antarctica. It's really focused on the United States, Canada, and Europe. And there are some implications here for vision and language models. Mostly that we've been training and evaluating on a narrow linguistic or cultural domain, and this gives us no real way of assessing their comprehension outside of the English language bias that we have here. And so in rethinking vision and language data, we went back to the start, and we want to collect a vision and language data set that can allow us to evaluate more languages and more concepts. And so there's a rich history in the linguistics and cognitive science literature on how people think about categories and concepts. We're going back to Aristotle, and we also have a line of very influential papers by Eleanor Roche. But one thing that's generally agreed amongst all the disagreements within this community is that categories tend to form a hierarchy. I'm showing an example over here on the right-hand side where we can think about going between superordinate basic level categories and subordinate level categories. And there's this common idea of basic level categories. But what it means to be different parts of this hierarchy and the categories or concepts people would use to assign to different examples is only somewhat universal. It depends on different cultures, and there's also this idea of the familiarity of individuals with the categories and the concepts. And so when you think about concrete concepts, In other words, things that are not abstract like democracy or freedom or love. Some of these are best understood within some kind of cultural background. And I don't want to spend the rest of the talk defining what I mean by culture. So we're going to take a working definition as the way of a collective of people that distinguishes them from other people. And there's a nice overview of cross-cultural strategies in NLP that will be coming out at ACL 2022. So I'd encourage you to look at that for a broader perspective on this idea of culture and language processing. But if we come back to these concrete concepts, then here are 3 examples that some of you may be more familiar with than others. If I asked you to describe the concept depicted in the first image, some of you will know this very quickly, and others, like myself, would probably just think this is some kind of sport. But if you're from the Basque country, then you would very quickly know this is pelota, or you might call it jai alai, depending on where you are. When we come to the second image, you might know what these instruments are. I would just call them an instrument. But if you're from China, you might call this a sanshan, or if you're from Japan, you might call this a shamisen. And this is a common and popular musical instrument within either of those countries. And so the final image is one that I don't think many of you would have any understanding of. You can say that it's something that's on fire and it looks dangerous. This is part of a pagan ritual that happens 5 miles away from my hometown. They fill this barrel with tar and they set it on fire and carry it around the street. I don't fully understand the reasons behind this, but it is a concept that's best understood within the cultural background of people who live within that area. And so one question you can ask yourself is, for all of the importance of ImageNet and COCO and Visual Genome and how they've advanced our field, to what extent are these concepts cross-lingual? So our idea here was to estimate this cross-linguality using Wikipedia as an approximation. And the way we do this is we take a concept or a synset, and we look for the existence of this in the English Wikipedia. And from there, we look to see whether it exists in other Wikipedias. So in this illustration, this particular concept can be found in Italian, and it can be found in Tamil, but not in Chinese. And so if we plot this across all of the languages that are available within this relationship map on Wikipedia, we would really like to see that all of the concepts in ImageNet are over to the right-hand side. But they're not, which means that not many of these concepts are universally represented in this approximation. Most of the concepts are only found in 30 or fewer languages, and there are only a very few number of more universal concepts. So already we can estimate that the ImageNet concepts will not be well covered in other languages. We can also ask ourselves whether they are overly specific, and we do this by mapping the human concepts from Ordonez and colleagues 2013 onto WordNet. And then we want to measure the depth at which the ImageNet label for an image compares to the human labels. And so for these examples up here with the American robin, you might just say bird if you were asked. Or for the Weimaraner, you might just say dog. And so what we find here when we look at the depth of the annotations is that the human annotations are less specific than the ImageNet labels within the English language. And yet we're using these really specific label sets in order to train our visual classifier models. So when we take all of this together, and we think about ImageNet in particular, the concepts that are used for the selection of images are very fine-grained, and this is controlled by the English ImageNet semantic hierarchy. The images that form part of the dataset were found using search engines with American English queries, and the cleanup of the annotated data was performed by crowd workers based in the United States of America. So we have a really strong North American English language bias throughout the entirety of this resource. In this paper that I want to talk about, we try to really go back to the start and see whether we could do something different there. So this is joint work with Fangyu and Emanuela, Eduardo, Shiva, and Nigel, a collaboration of people from the University of Copenhagen, Montreal, and Cambridge. And so the major outcome of this work is a resource and a method for collecting data for multicultural reasoning over vision and language. We have a collection of images that are representative of the annotator's cultures, and we collect this data over 5 typologically diverse languages, where we have independent and culture-specific annotations. In this example here, by coincidence, all of the annotators agreed that basketball was an important part of their culture. And we have these images of what basketball looks like in these 5 different languages. So in terms of the data collection process, which is an entirely native speaker-driven protocol, we start off with these 5 languages: Mandarin, Swahili, Tamil, Indonesian, and Turkish. And we ask our crowd workers to select concepts. And after that, we ask different crowd workers to select the images that represent those concepts. And then in the final stage, we ask them to make textual annotations that we can use for downstream machine learning tasks. So this downstream task is a visual reasoning task, first proposed by Sur and colleagues in 2019. And what we're looking for here is a data point where we have 2 images that are paired with a sentence. The sentence in our case is written in the native language of the annotator, and this is Tamil, and we're providing a gloss here so that you can understand the sentence yourself. It says, in one of the 2 photos, more than 2 yellow-shirted players are engaged in bull taming. And so the task that we will ultimately work on in a machine learning setup is to predict whether the sentence X is a true description of the pair of images V1 and V2. And the data we collect, like I said, is this native language data in Tamil or Indonesian or Mandarin. It's not this translated form that you see underneath the caption. In terms of the concepts, MaRVL is created from a set of universal concepts taken from the Intercontinental Dictionary series. We focused on the chapters that are concerned with concrete objects or events, so things like animals or the house or cognition or religious beliefs. We don't include more abstract chapters because the dispersion over those types of images is expected to be much higher. And this is where we introduce a bias into the process. We can't escape this type of bias, but by using the Intercontinental Dictionary series, we've tried to minimize the effect of it. So in step 1, we have this language-specific concept selection, and we ask native speakers to give us a set of concepts that are commonly seen or representative of their culture, and they should be ideally physical or concrete instead of abstract. So the way this process works is that we select a semantic field from the Intercontinental Dictionary series, for example, sport. And then we have a set of native speakers of that language, and we ask them to find examples of this on Wikipedia pages. This is also a bias we introduce, and it's just so we have something we can concretely refer back to later and that could be used in other experiments. So we ask them to identify 5 to 10 of these concepts, and then across the annotators, we take the top 5 per semantic field, and we end up with approximately 90 of these concepts per language. And if we take a high-level look at the resulting concepts that we collect, in some cases, up to 25 of them are not present in the English word net, which we think is quite an interesting result. And if we collected even more data, I think that this number would probably stay proportional to that. So now we have our concepts from our native speakers. We need to collect the images. And this is also done by native speakers, where we want them to give us images that contain more than one instance of the concept, where it shows an instance of the concept interacting with other objects rather than in isolation, where, if relevant, the instance of the concept is involved in some kind of activity. And it should display some kind of diverse objects or properties. So instead of just putting the raki in isolation, it's in the context of how you may enjoy a glass of raki. So now we have our image collection from our native speaker crowd workers, and we move on to the language annotation task. And so here, with all the images that we've collected, we'll pick a concept. This might be table tennis. And we ask a crowd worker to write a caption that's true for only 2 pairs of these images. And in this case, our crowd worker identifies that they can write a caption in Mandarin that describes the 2 pairs on the right-hand side. A different crowd worker validates these annotations. If they are incorrect or there's a problem with it, it goes back to the caption writing stage. Otherwise, it becomes a part of our final data set. And for those of you who don't speak Mandarin, perhaps you like me, I don't speak this. The gloss is that the man in the right image is serving a ball, while the man in the left image is returning a ball. And agreement on whether the captions are accurate descriptions of the image is a reproducible outcome, and we have high inter-annotator agreement here. So this is the end of the dataset collection process, and I'd like to show you some examples of what we have. Here's an example from Turkish of the concept kanun. The Turkish caption is the original, and the gloss reads that in one of the images there are multiple people with kanuns on their knees. And so the answer to this is true, and the image that would explain this is the image on the right-hand side. Another example taken from Tamil is this pair of images here, which represent this concept of vada. And the statement is that both images contain lots of masala vadas. I don't actually know what these are, but speaking with Shiva, one of the collaborators on the project, vadas are these things on the left-hand side, and so the answer here is false. So in summary, wrapping up this kind of data collection phase of MaRVL, we have 5,500 data points across these 5 typologically diverse languages, covering 423 concepts in total, of which 96 of those were not found in the English WordNet. And there are 1,390 unique captions produced by our annotators. Overall, MaRVL covers more languages than other similar resources like ImageNet or the English NLVR2 in terms of the existence of concepts in other languages. And as a result, it covers more language families and more macro areas. One of the things that can be quite challenging for collecting MaRVL data is finding crowd workers for lower resourced languages. And this is something where I think maybe we could collaborate with universities or researchers around the world to collect this in a more scalable fashion. And also that using Wikipedia as a proxy for whether the concept exists is a requirement that we'd like to relax in the future, because it seems like for lower resource languages, their Wikipedias might be smaller, and this could unfairly affect the types of concepts people would prepare for us. So now that we've collected all of this data, we want to model it for some kind of machine learning task. In other words, this visual reasoning task. And to do that, we're going to use a vision and language BERT. A vision and language BERT model takes a sentence and it wraps them in these special classifier and separator tokens using a pre-trained language model tokenizer. The language embedding then is used as an input to a multi-layer transformer to obtain these output embedding representations at the top layer. Now, the visual data can be integrated into this transformer model by, first of all, a common approach is to extract features from a fixed or variable number of regions of interest. These are commonly found using an object detector. And from each of these regions of interest, we embed these as an input. And then we reuse this transformer architecture to jointly encode the language data and the visual data. And similar to language modeling, we have a masked language modeling task in the presence of the visual inputs. It's also common to use some kind of image-based objective, like classifying the properties of the region that's masked in the image, and also trying to match image and text similar to the next sentence prediction that was originally proposed in the BERT paper. And in terms of what's in this transformer body, there are a lot of different options out there. I'm only listing 8 possible options here, but this could have gone on for much longer. And so I want to try and explain to you what I think is some of the most important differences between these models. And that's based on whether they have a single stream or a dual stream architecture. And what I mean by this is that in a single stream architecture, the image inputs and the textual inputs are concatenated together. So we have a single data stream for the input, and the transformer layers attend over all of the language inputs and all of the textual, the visual inputs at each layer in the model. And this is from the input side to producing the output embeddings. These dual stream architectures, first of all, will process the image and the text independently using modality-specific transformer layers. And so this is usually the first K layers of the model after the embedding. And then there are cross-modal layers that are either based on intra-modal attention. So this is, once again, just processing the data independently, or intermodal attention, where given a query in one modality, the keys and the values are taken from the opposite modality. And so you force this cross-modal representation learning. And a common strategy that we've seen in the literature is to interleave the intermodal followed by the intramodal attention for a specified number of layers when building these architectures. So given all of these choices you can make about single stream versus dual stream architectures and how do you embed the inputs and which tasks do you train on, a common question that people ask is, are these models actually cross-modal? And so last year we tried to answer this question by using a crossmodal ablation study, where we want to test how a missing modality affects model behavior. And so in this case, we can imagine the simplest setup where we don't ablate any of the input. And in this case, we're not ablating the visual input, and we want to predict the identity of the masked token. So we would do a forward pass of this through our vision and language model, and then try to estimate the probability of this masked token being the token girl. We can have a really extreme example on the other side where we fully ablate the visual input by reducing it to noise. With the same language input, we can also push this through our pre-trained model, and we would expect that if they're actually cross-modal, then performance would decrease quite a lot here. In a third setup, we might ablate only the visual inputs surrounding the object. And in this case, we would expect there to be performance somewhere in between fully ablating the input and not ablating it at all. So we run this analysis in a dataset where we know the alignments between bounding boxes in the image and words in the text. And the answer is that it's complicated. So this graph here is showing the change in masked language modeling performance when we ablate visual data. So on the left-hand side, we have none, which means none of the visual data is ablated, and that's the model as it would be used in practice. In the middle, we have this setup where we ablate the object that should be aligned with the language masked identity and process. And so here we can see that performance drops for all models. So they are really being affected by not having access to the aligned visual data. And when we throw away all of the visual input, then the performance is much worse. It's actually even worse than using a pure language model that's pre-trained on the conceptual captions dataset of images annotated with sentences. And so what we can conclude is that we get lower performance when we ablate visual information from this model. But when we look at the other side and we try to determine what happens when we ablate textual inputs, when we're predicting the visual properties of masked regions, then ablating the language phrases does not have nearly the same effect. And so the main conclusion that we have from this is that these models are mainly learning to use vision for language. And by these models, I mean LexMERT, VLBERT, VisualBERT, and Unitar. We haven't tried this for some of the more recent models, which are trained on a lot more data or are a lot larger. But I think the code for this project is online, and if you're interested in that, you can try this yourself on your own model. Another question that commonly comes up is, which of these models should I use? If there are so many of them available, does it actually matter? In one of our studies, we looked at what happens if you control for the amount of pre-training data the model sees when it's being trained. And so the rhombus shapes are the performance on the visual question answering task when you use the original amount of pre-training in those papers. And you can see that each of these rhomboids have very different sizes, and the performance on the downstream task varies quite a lot as well. But when you control the amount of pre-training data, these models actually perform much more similarly to each other. There's a mild deviation here for the LexMERT model, but when it comes to VilBERT base, VisualBERT, and Unitar base, there's a lot more in common across these. And so in the remainder of this talk, when I present the experiments and the results, I'm going to talk about what we find for using Unitar base and its architecture as a starting point for our multilingual and multimodal models. So now that I've spoken about all the data we've collected for MaRVL and how we've tried to make it really multilingual across different regions of the world, and I've explained the different types of vision and language BERTs we're going to use, now I want to tell you about some of the experiments we performed and the results we found. So the first step is to explain how we pre-train our models. We have 5 English vision and language BERTs implemented in the Volta framework, which was developed here at the University of Copenhagen. And we also have 2 new multilingual Unitar-based models. We have MUnitar, which is initialized in its architecture from multilingual BERT. And we have XUnitar, which is initialized from an XLMR starting point. In terms of the data, for all of the models, we use the English conceptual captions dataset, which is about 3 million images, and we pre-train on masked language modeling, masked region modeling, and the image text matching objectives. For M or XUnitar, we also have a language-only masked language modeling task, over 104 Wikipedia datasets, and this is to prevent the models from forgetting how to model other languages except for English. After we've pre-trained the models, we'll fine-tune them for this visual reasoning task. And we're going to use 86,000 data points in the English NLVR2 dataset. We don't have this data available in any other language. And then we'll test on our 5,500 data points in MaRVL in either a zero-shot setting, where we use the multilingual inputs directly in a cross-lingual approach, or in a translate test setting, where we use the English models by machine translating the language data from, say, Indonesian into English or Swahili into English. So let's get into some of these results. We start off with a sanity check. How well do our new models perform on the English NLVR2 dataset? So these are the Vision and LanguageBERTs implemented in Volta. And the two models that we have implemented, MUniter and XUniter, perform similarly to the English models. There's about half a point difference for MUniter and about 0.8 for XUniter. But I think this is actually okay, given that these models have to encode a lot more languages into their parameter space. And the curse of multilinguality is something that's well established in these different setups. So now that we've passed this sanity check, let's move on to results on our MaRVL datasets. We have our zero-shot results, where we use the MUniter or XUniter model directly with the original languages. I'm re-showing the English results here for context, and the performance for the other languages is really bad. So for each of them, we're around like a little bit above chance level, but not substantially. And this substantial drop in performance is something that we didn't necessarily expect. But what you can see is that when we take this XUniter model, it generally seems to be better than the MUniter model, with the exception of Chinese Mandarin. Now, in the translate test setup, I'm going to show you a collection of different models as our kind of anchoring point. These are the English results from the sanity check. So we're going to translate all of our data into English language and evaluate it on these 5 different English language models. So we'll start here by showing the result for Mandarin. The performance here is much closer to 60% for some of these models, showing that as we translate this data, the performance is much better. And this holds across Tamil and Swahili and Indonesian. The one outlier here is Turkish. And in Turkish, the performance may be much higher than other languages because the types of concepts selected by our Turkish annotators are more in line with the concepts in the English NLVR dataset. But overall, the translate test setup is much better than the zero-shot transfer. So it is possible to do something useful on this task. You might be wondering, why is MaRVL so difficult? We think it's because there are 2 types of distributional shift. One is that you have to do cross-lingual transfer in the zero-shot setup. And in both cases, you have to deal with out-of-distribution concepts. And so we can explore the effect of this by filling in different results within this grid. If we look at the top left part of this, if the concepts are in domain and we are evaluating on the same language that we train our model on, then we have our NLVR2 result at 72.8% accuracy. In the opposite corner, we have the result for MaRVL, where our test languages are all different than the language used to train the classifier, and the concepts are out of domain. In the top right corner, this is where we have the cross-lingual transfer problem. And to evaluate the contribution cross-lingual transfer makes, Fangyu manually translated from English into Mandarin 1,000 examples. And we see here about a 15% drop in performance compared to using the English language examples here. So this is a big difference. And this number is probably underestimated because it's such a small sample compared to others. But it required the work of a native Mandarin speaker and a fluent English speaker. So we're happy that this is a reasonable estimate. We can also go in the other direction, where we take the examples in the MaRVL Chinese dataset and we ask Fang Yu if you could translate these into English, and we get an 8% drop in performance there. So there's still a difficult shift here when we are within the same language, but now the visual concepts and the language concepts are difficult and different. And we can also explore what happens if we just machine translate all of the NLVR2 data from English into Chinese. And the performance here is still quite low. It's a hard shift in this case. In fact, both of these distributional shifts are really challenging to overcome. And I think this will give us opportunities for a lot of exciting research in the future, whether you're interested in the effect of cross-lingual transfer or modeling out of distribution concepts. So I'd like to wrap up now with some final words. I'll start by acknowledging that there are definitely some connections to related work. This project kind of tackles lots of different issues. There are some known results in machine translation on the effect of translation direction or translation ease. There's also been some ongoing work on multimodal image and text learning. Within the more direct multimodal learning space, concurrent to our own work, we saw 3 other pieces of work in the same year on geographically diverse common sense reasoning, on visually grounded question answering, and on huge scale multilingual image text retrieval. And in the computer vision community, we saw a geographically diverse replacement for the ImageNet hierarchy that also was trying to be GDPR compliant. And I'm sure there are lots of other connections to the related work that I'm missing here. And so if you know of some, please reach out to me. I'd be very happy to read the work and to understand its connection to what I've been discussing today. In terms of future work, I think there are 3 major directions that we're looking at. One is, how can we refine the data collection process? This is just our first attempt at it. All of our guidelines are available online. But I think that we could perhaps streamline this and make it possible to scale this up to collecting more data for more languages. In terms of a modeling direction, I think we need to start pre-training on data that goes beyond ImageNet, visual genome, or conceptual captions. And this is because we need to be able to deal with concepts that are not seen within the kind of classic ImageNet, WordNet hierarchy. And in terms of tasks, we've only presented one type of task here, which is the visually grounded reasoning task. And I think ultimately we'd like to see a bit more variety in the multilingual multimodal task space. On the third item, we have been doing some work in this direction ourselves. We recently shared a preprint of an approach called Igloo, where we collect multilingual vision and language tasks for 4 different types of tasks, be it reasoning, question answering, retrieval, or natural language inference, covering a large number of language families and scripts, and whether we have training or evaluation only data for these. And there are a huge number of results that we've tried to calculate over this as a starting point. And one observation I'd like to share is that it seems quite challenging to do few-shot learning within these setups. And this is something that I think will be quite important when working outside of English language, multilingual and multimodal data. So in conclusion, today I've been speaking about going back to rethinking vision and language data at the level of the concepts that are depicted in the images. And I highlighted the fact that existing vision and language datasets tend to have a North American or European bias. I presented a new protocol for creating data that's driven by native speakers at each step in the process. Out of this, we produced MaRVL, which is a vision and language reasoning dataset across 5 typologically diverse languages. And the 2 multilingual BERT models that we presented perform at chance level in the zero-shot cross-lingual transfer setup. showing that there's a lot of room for research and development in this area. I'd like to finish with just a high-level thought that I think the work we have here has implications well beyond language and vision research. I think that multilingual datasets should not just be translations of English data. This is a message I see as I read more of the literature in this area, and I think that we should continue to take these ideas seriously. Thank you very much. I'm happy to take any questions.
No, thank you, Desmond. So if you have any question, just raise your hand. I think you have a button below in your screen, so I can just pass the control and pass the microphone just to speak, okay? Okay, I think Eneko has a question there. Okay, Eneko, you can speak if you want.
I don't hear the question.
Yeah, and Eneko, we can't hear you, so. Okay, in the chat. Okay, so if any other has any question, just I think you can directly, you have the microphone, so just you can speak and ask the question.
Thanks, Desmond. I'm not putting the video on because I'm a bit sick at home, so very, very good work. I wanted to ask you about a bit more information about the M and X models because I didn't quite catch that.
Sure. Could you be a bit more specific about what you would like to know?
Like how they work, because these are the models, like the I think they were called M uniter and X uniter, right? So yeah, just to know how they work and what the difference is between them.
Sure. So both of these models are single stream vision and language BERTs. And that means that they process the image inputs and the language inputs as one common input. They have attention across all of these inputs at every layer. And the main difference between them is whether we initialize the parameters and thus the architecture from MBERT or from XLMR. And when we initialize it from XLMR, we have a much larger language vocabulary of, I think, 250,000 subword tokens. Whereas in MBERT, it's much smaller than that. And in some of our experiments on other tasks, having XLMR as the base is a much better starting point. Does this answer your question, Gemma?
Yes, thanks.
Thank you. And Nico, I still don't hear you. Okay, I see that Lucia Donatelli has written a question. Lucia writes, "Thank you for the talk. My internet is also unstable. Apart from probing BERT, do you have thoughts on using intermediate representations to offer explanations of how our models make decisions on the tasks you mention? I know of many intermediate language representations, but I'm not familiar with vision representations." Thanks for the question, Lucia. I don't know of many commonly agreed intermediate vision representations that you could use here. So there are things like these scene graphs from Stanford University, which are at the heart of the visual genome dataset. Some works actually try to use these scene graph structures as biases that they encode into their models. So if you actually do that, then I don't know if it makes sense to try and pull that out at the end. But perhaps this would be one approach you could take. You would use scene graph representations, which would tell you about the relationships between objects, and you could determine whether a vision and LanguageBERT would predict a similar set of relationships, perhaps by probing for them or directly examining them using something like attention rollout. I'm not sure if this would really tell us what we wanted, given that sometimes you can have these single stream models or dual stream models, and what happens at different layers in them would be very different. So maybe you would end up having a really large expedition of trying to find something in the model that may or may not exist. I hope this somewhat answers your question. And if it doesn't, please feel free to follow up. Okay, so I have a question here in the text from Eneko. On slide 26, could you explain what masked region classification is? I can. So let me see if I can find this slide again. Yeah. Okay, so I'll share my screen with you, and hopefully you can see a slide called "It's Complicated." So let's go back to slide 23. The faster RCNN object detector we've primed it to predict the existence of 36 regions of interest. And this is a bounding box where within that bounding box, the object detector predicts a probability distribution over about 1,500 different types of objects or properties of objects. And so for this, let's imagine that it managed to find this dragon region in the image. We would do a forward pass using our vision encoder to extract a fixed dimension vector to represent that at the input. And then as an output, we would have this probability distribution over these 1,600 regions of interest. And so when I go over to this slide here, and I talk about masked region classification, we explore two different setups in this study, which was led by Stella Frank. You can either determine how accurately the model predicts the maximum probability object within a region, or you can see how well the probability distribution across that is predicted by the model. I see that you've written a comment. Let me stop sharing my screen. I mean, how is this linked to the language for vision versus vision for language? So if in the masked region classification, we are trying to predict the distribution over the expected objects in a region, does language input on the BERT encoder actually help with this? So let's imagine that the region is supposed to be about a dog. If the model sees the word dog in the sentence, does that affect how it predicts the probability of that region being about a dog or not? And in this result I showed here, where you go from having all of the language available to ablating the language inputs, the performance doesn't change very much. And we believe this shows that it's not forming this link in using language for vision. Thanks for the question.
Okay, more questions? Okay, I have just one question. So you are building this data set. Okay, Thierry, you can ask if you want.
Oh, I can wait until you are done.
Okay, no, my question is that, so you're building this data set just to control the cultural bias and avoid this the bias that is in English culture in this data set. But what would we, I mean, I guess that we should do similar thing with the language models. I guess that this multimodal language model, multilingual language model that you are using in the experiment, they have some kind of bias towards English. I guess that, the corpus that is trained is basically, the biggest part is English. So this could affect, or how we could control this.
Yeah, I think this is a relevant question. When we take something like XLMR, when they showed the distribution over the language data they used to train it, it is skewed towards English. And so they do propose a sampling technique when they are training XLMR to try and confirm this kind of proportional representation of language within the batches. And in their paper, they do talk about this. They note a problem about the curse of multilinguality. As you try to squeeze more and more languages into a single encoder, the performance tends to drop.
Yep.
I think that some approaches we could think about to alleviate this problem would be maybe based around having language-specific adapters within our model. This might be a reasonable approach. But it also might be something that it doesn't scale very well as we want to train with more and more languages.
Yeah.
I do not have a straightforward answer, but I
Okay.
think it's an interesting problem to think about.
Yeah. Okay, thank you, Ed. So, Thierry, if you
yes,
want.
thank you. Desmond, first of all, thank you for the very informative and clear talk to me. I learned a lot. My question is less technical. You were mentioning cross-cultural and cross-lingual. And my question would be how far there is overlap. So, for example, Spanish in Bolivia and Spain, also on, and I was over in Mexico and Guatemala that they use the word camion for distinct objects that are related somehow. So how deep do you go into the really local aspect of language dealing with different cultures, basically?
So thanks for the question. In this work, we do not dive deep into that at all. I think it would be really interesting if you wanted to take Spanish as an example, where you could take European Spanish versus different South American Spanish speaking countries, and to collect data at that kind of level of granularity and see how well models would transfer across those different setups. But it's not something that we've done here. And I think to do that, you would need to have a really well developed data collection procedure where maybe you weren't crowdsourcing anymore, but you had found some kind of gamification where people actually really wanted to share their data with you. With all the concerns around GDPR and personal information, this is something I have not yet figured out how to do, but I think it would be a fascinating direction.
I would like to see it.
Yeah, I would like to see this
thanks
too.
again for the nice presentation.
Thanks, Thierry.
Okay, so more question. The last question. It's 4 o'clock already. Okay, I guess that if we don't have more questions, we can finish here the talk. So yeah, thank you, Desmond, for a very interesting talk, and yeah, see you soon. Thank you.
Thank you, Ayer, and thanks for the invitation.
You're welcome.
Bye.